Hello everyone. In this lab project, we are going to verify the truth table of the digital gates. So first we start to simulate in Multisim and verify the truth table. Then we actually move to the breadboard and make the same circuits and also verify the truth tables in the breadboard with TTL ICs. So if you didn't watch my previous video, which I explained about the digital gates, please watch that video that is in the course YouTube channel. So let's start with the AND gate. So as you could see here, we have the AND gates. We have two inputs. We actually add two switch. One side of this switch connected to the 5 volt or digital 1, the other side connected to the ground. Same thing for the switch 2. That means whenever I change the switch, it's somehow switch between 0 and 1, and I able to give 0 1 to these input that you see. And say similarly for input 2, I could actually give 0 1 through this switch. So first, let's do verify the truth table of the AND gate. So I actually use the AND gate. So in Multisim, if you click on the select the component, so here you could see the different family in here in the group. You could go and select the TTL and the 74 series. You could actually select any digital component that you need to simulate. Okay, so here we use actually three component. So the first one is the switch, the next one is the AND gate, and the third one is the indicator. So let I just bring this back here and a little zoom it. Okay, so if you you never work with the multisim, so that you easily you could find these component. So for getting these TTL gate, you need to go to the group TTL, and the family is 74STD and component is 7408. So that means you click in one of these icons. So here in the group, you go and find the TTL. So in TTL family, go to the 74ST, this family, and 7408 is AND gate, okay? So for getting the indicator, so in the group, you could go to the indicator. So see in the group, we have the indicator. You select indicator. So inside the integrator, in the family, you need to choose probe. So family probe, and you could select probe DIG red or blue. Any of them is actually acceptable. So the third one that you have is the switch. So in this for finding switch, you back here goes to the group basic. So in the basic groups, you go find the switch, and in the switch, you go find the SPDD. So these SPDD is the switch that I used. And source for the VCC and ground, which is easy, you go to the group should be source. If you back here and find the source, that is source. So you need to find the family power source. So power source in the family, and the ground will be the ground that you have. So see, this is a ground that you could select, and also the VCC that you have. So one of these could be, or these reference could be acceptable. So yeah, see, whatever I used is the VCC. If you want, you could get the same thing that you have. So this is how you could select them. So then you wire up between different component, and finally you could simulate that. So let's do simulate and see it's actually work based off the AND truth table. So what's happening in the AND gate? So if you remember the truth table, whenever one of the input is 0, the output should be 0. So see, right now I have 0, 1, the output is 0. If I give 1, 0, again it is 0. If both is 0 is 0, the only case the AND is 1, it is actually both should be 1. The both is 1, it gives you a 1. Whenever this is on, it means this is 1. Whenever it is off, it means it is 0. So see here, I actually verified the truth table of the AND gate. So you do the same thing for the other gates that we have. So I'm coming back here. I just stopped the simulation back to the OR. So this is the OR. So as you could see, similar things. You have the OR to switch, which give you 0, 1 to inputs, and the output, which is an indicator. You could see that's 0 or 1. So the truth table of the OR gates, if you remember, the output is 1 if one of your output is 1. So here both is 1, the output is 1. So here this is 0, this is 1, again give you a 1. So again, if you 1 again is 0 and the next one is this one is 1 and this one is 0, again should be 1, because this is the OR. The only case OR is 0 is both should be 0. So see, I put the both on the 0, so you got the 0. So I verify the truth table of the OR. So go to the next gate is not just has one input, so that's the reason you just need one switch. So whenever you have 0, it should give you a 1. Whenever you have 1, it should give you a 0. So right now it is 0, it's not is 1. Whenever you have 1, it's not is 0. So it works. So I verify the truth table of the OR. Next gate is the Nand. So Nand is actually a AND which has the NOT at the end. So similarly, we have two input with two switch. We give 0, 1 and verify the truth table. So see, start with 1. Whenever both is 1 and 1 is 1 and it's not is 0. So that's the reason it is 0. If I change 1 to 0, 0 and 1 is 0, it's not is 1, it is right. If I switch between 2, again 0 and 1 and is 0, not is 1, that's right. If I put the both to the 0, 0, 0 and is 0 and it's not is 1. So that means the only case it is 0 is whenever both is 1, because and 1 is 1 and it's not is 0. Otherwise, it's going to be 1. So you verify the truth table and check the all 4 different bit pattern you could have in the input. So this is NAND. Let's go to the next, which is NOR. NOR is the OR, which has the not in at the end. So let's to simulate that. So whenever 1 is 0, the next one is 1. So OR is 0 or 1 is 1, it's not is 0, that's right. So that means whenever both is 1, again 1 or 1 is 1, it's not is 0. So if you change that to 0, this is 1, again 1, 0, 1 is or is 1, not is 0. The only case it's actually changed to the 1 is whenever both is 0, right? Why? Because 0 or 0 is 0, it's not is 1 and it is on, and otherwise in the all other cases, the output should be 0. The only case it is on is actually the both is 0. So we actually verify the NOR. Let's do stop these here and check the XOR. First, let's do check the XOR and simulate that. So if you check the truth table of the XOR, so in the XOR, the output is 0 whenever the both input is the same. So same means both is 0 or 1. So right now it is different, they are 1. So if I make that different, again this is 1. So the only case is the 0 is both same. So right now it's same, both is 1, it is 0. Again the both is same, you have actually 0. So which is somehow we verify the XOR. So and finally XNOR, let's do check the XNOR too. So let's do first back to the XOR and stop the simulation of the XOR and back XNOR. XOR is the opposite of the XOR, right? So whenever the both is same, the output is 1. Whenever they are different, the output is 0. So that means whenever both is same, so right now the both is, yeah, we need to start to simulate. Okay. So whenever the both is 0, the output should be 1. That's right. Whenever both is 1, output should be 1. Whenever they are different, the output should be 0. So this is a truth table of the XNOR. So as you can see, I checked the all 4 different input for the XNOR, which is match base of the truth table that we learned in digital gate video. So this is how you could verify the truth table with simulation for the all digital gates. So in the next step, we are going to use the TTL ICs and verify these same truth table on the breadboard with the gate ICs. So before to do that, you could actually go to the Google and just Google the digital gates IC number. So if you just Google that digital gates IC numbers, it's actually give you a tons of the pictures, which is give you what number you have for each gate. For example, if you take a look to this one, and if I click on that, so as you could see here, yeah, so see here you could see the name of the IC. So as I mentioned, you could actually check any of them. So for example, this one shows the 7408 is the IC number, has 4 AND gates. So see, input 1 and 2 is the input and the pin 3 is your output. You have actually 4 IC inside, 4 AND gate inside the 7408 IC. So usually there is a notch in one side of the IC, which is it's corresponding to the pin 1. You go to the 7, you back to the 8 and 14. Just be careful. In most of them, pin 14 and 14 is VCC, and this is ground. You connect this to the ground, and this VCC should be 5 volt. So similarly, 7432 IC is OR gate. You have 4 OR gate inside these IC. You could use any of them. So what we are going to do, we are going to connect our switch to pin 1 and 2 and connect these pin 3 to the LED. Give a different value to input 1 and 2 and see what's the result of the output. Similar things that we did in simulation, but here we use our workbench because our workbench able to use the input 0 and 1, and also we able to check the output, which is 0 or 1. If you didn't watch the our digital workbench video, please watch that video, which I explain how you could make the simple workbench for a digital lamp, which we are able to have input ports and output ports. With the input ports, you are able to produce 0, 1, and with the output port, you could check which value is 0 and 1 in your output. So similarly, so 7400 has 4 NAND gate, so 7400 has 4 OR gate, and XOR is 7486. So this is its map. You could know which one should be input, which one output. So 74266 is XNOR. So this is the pins, and finally 04 is the NOT gate. So as you can see, if you put the switch on 1 and LED on 2, you are able to verify the truth table. So you put each of them on the breadboard and you verify the truth table by giving the different inputs to each of them and watch or observe the output. So whatever you see should be matched based on truth table that you already know. So let's do that. Let's go and implement these circuits on the breadboard and see how you could verify the truth table of the 7 gates that we have. So after a simulation, we want to verify the truth table of the all gates on the breadboard and using the ICs. So as you could see here, we have our workbench, which is, if you didn't watch the previous video, which is I explained how you could make a workbench for the digital lab, you could watch that video. So what you have here is the small workbench. You have one switch here, which is this side of this is input ports. So if you connect any wire here with changing this switch, it's able to give you a 0, 1 here in these input ports. You have also have the output ports. If you connect the output here, if your output is 1, this LED will be on. So if the output is 0, this should be off. So as you see in the simulation, we start to work with first gate, which is the AND gate. So whatever I have here is my AND gate. So the IC number is 7408. So if you just search for the 7408 IC datasheet, you could see the pin map of the IC. If you take a look at that pin map, so usually we have a small notch here on one side of the IC. So here this is pin 1, 2. So this should be 7. The other side is 8. And you have 9, 10, and until you get the 14. So again, if you take a look to the data sheet, so the port 14 should be connected to your VCC, which is we did here, and port 7 is the ground. So without these ground and VCC, these IC doesn't work. So that means your gate actually doesn't work. So according to the data sheet, so the pin 1 and 2 is the input of your AND gate, and the output is actually pin 3. So that means if I want to verify the AND table, so definitely I need to two input for the AND. So inside these IC, again, if you check its datasheet, you could search from the internet. So there is actually in 7408 IC, inside this you have 4 AND gate. So the first one AND gate is the input pins is 1 and 2, 3 is output for second, and pin 4 and 5 is input, and 6 is output for the third one. Pin 10 and 9 is input, and 8 is output. And for the fourth one, pin 13 and 12 is your input, and the 11 is your output. So that means inside these IC you have 4 AND gate. You could use any of them that you want. We start to use the first one. For the first one, the input is pin and 1 and 2. So I connect one wire to pin 1 and another one to pin 2. So then I connect this to my input port, which is able to give 0 and 1. So this is actually for the first input pin. This is a second one, okay? So that means whenever I change these two switch, I'm able to give to pin 1 and 2, which is the input of the AND gate, 0 and 1, okay? So definitely you need the output to see what's the result, because you want to verify the truth table. So the pin 3 is my output for this gate, AND gate. I connect the jumper wire to pin 3 and connect to these one of these LEDs, okay? So it's on. So there is a reason, because these right now, these two switch is on the other side. Whenever they are on this side, they give 1. Whenever I change to the other side, they give actually 0. So right now I give 1 and 1 to the gate, and the AND 1 and 1 give you a 1. That's the reason you have actually these LEDs on. So that means the case 1 and 1 give you a 1, it is right. So based off the truth table, if one of the input is 0, definitely the output should be 0. Let's do test that. I change that to the 0, so the output is 0, the LED is off. Again, back here and turn another one. So again, whenever one of them is 0, the output is 0. If the both 0, so I've actually put the both 0, so the both input is 0, the output is 0. So it works, right? I verify the table. The only case that this is on whenever you give to 1 and the LED will be on. So that means 1 and 1 is 1. If one of these input is 0, definitely the output should be 0. Let's see, whenever I keep 1 0 to one of the output is 0. Okay? So you need to, in the similar way, you need to convert the truth table of the OR. So the OR IC is 70, the IC number for OR is 7432. So you need to verify the Nand, which is the IC number is 7420. You need to verify NOR, which is the IC number is 7402. You need to verify XOR, the IC number is 7486. And also the XNOR, which is the IC number is 74266. And finally the NOT gate, which is the IC number is 7404. So I'm show two more. I show you verifying the OR. I have OR. I have actually here I have the NAND. I have here the all others. I have NOT, XOR, XNOR. But if you get how you could verify one of them, you could do the all others. I show here 3, and you do the rest yourself. Okay. So now let's verify the truth table of the OR gate. So this is the OR gate. So the IC number is 7432. Again, if you search in the internet, in the Google, just write the 7432 pin out. You get the, from the data sheet, you could see the map. So here, whenever you have these small notch here, so these pin will be 1, next 2, 3, 4, 5, 6, this is 7. So the other side you have 8 to 14. So similar with the AND, so according to the data sheet, the pin 7 is ground, and also 14 should be VCC. We put actually ground and VCC. Similar with the AND, inside this 7432, you have 4 OR gate. The first one, input is 1 and 2, output is 3. Second one, input is 4 and 5, output is pin 6. Third one, the input is pin 10 and 9, and the output is 8. And the fourth one, input is pin 12 and 13, and output is 11. You could use any of these 4 that you have, but again, we use the first one, which is input is 1 and 2, and the output is number 3. So let's just here we move the wires. So this time again the input should be comes from 1 and 2. This is pin 1. So this is pin 2, and these 3 are moved to these actually pin 3. So that means again same thing. You are actually able to give the input with changing these 2 switch 0 1, and this will be your output. So for the OR gate, so same things. If you check the truth table of the OR, if one of the input is 1, the output is 1, and the output is just 0 whenever the both is 0. So see right now, so the both is 1, this is 1. If I change 1 to 0, so it's still this is 1. So if I change another to 1 and another 1, 0 again is 1. So the only case is 0 is both should be 0. So which is this case. So the both is 0. You have the output is 0. If you turn one of them on, so it should be 1. Again, if one of them is 1, is the output is 1. Even if both is 1, it is 1. So the only case it is off in the OR gate is the when the both is 0, the output is 0. So this is for OR. In the same way, you could actually test all of them, but let I just do one more, and you could take care of the rest yourself. So the next IC that I have is 7420, which is the NAND gate. So in the NAND gate, you have inside the IC 7420, you have 4 NAND gate. So again, the first one is input is pin 1 and 2, output is 3. Next is input is 4 and 5, output is 6, the third NAND gate input is 10 and 9, the output is 8, and the fourth one is 12 and 13, and output is pin 11. So we use the first one. So again, this one, this is pin 1, this is pin 2, this is 3. So let's just move our input. So here you have the input, and you have 2 inputs goes to your switch, which give you a 0, 1, and 3 is your output. Okay. So the NAND, if you check the truth table of the NAND, so somehow NAND is the AND then 1 not. So that means the only case it should be 1 in the, if this is actually the AND, the only time give you a 1 is the time that both is 1. So because this is NAND, so the only time it gives you 0 is the when the both is actually 0. So let's do test that. So right now, let's do change both of them to 1. So 1, 1, and is 1, not is 0. So that's, you have nothing. If you turn one of them, so 0, 1, if you AND 0 and 1, the AND is 0. If you take not, it is 1. That's right. If you switch these two, there should be the same. 0, 1, and is 0, not is 1. That's right. And finally, if you put both on a 0, 0 and 0 is 0, it's not is 1. So you actually verify the truth table of the NAND. So you do the same thing. So I put these ICs here, which is the all other 4s that we have. So you could actually verify their table in the same way that I did for these 3 gates that I have here. So thank you for watching this video, and I hope you like this video.